I think we are ready. Good evening, everybody. I'm very sorry, I almost apologize, but I'm afraid you will have to go through one more talk before you get a sumptuous dinner. So I tried to make it as easy as possible. I'm going to phrase it in terms of a question here. So the question I would like to ask and answer is there a new dawn for micropolar fluid theory? What I'm going to do in my presentation is first of all remind you of two well-known theories. There is one by Ehringen and then there is another one by Ericsson and Leslie, which are very well known for the description of liquid crystals. And they agree to disagree. So there is a strong controversy between these two theories. And this is why I'm saying a new dawn, because we have Lena here, and she has proposed with the other Elena, an equation which might help to solve this controversy. So, without further ado, let me show what I plan to talk about. First of all, we are going to give a little motivation. Why do we use generalized continuum theories for materials with an inner structure, with inner degrees of freedom? And the example we are going to look at is liquid crystals. Then I'm going to dwell upon the theoretical foundations. I will introduce you to the champions of micropolar fluid theories, and then we will talk about number one, which is the Ehringen theory, and then not number two, but here the second one, the Ericsson-Leslie theory. And we will see that they, as I said before, they agree to disagree. So then finally I'm going to talk about a proposal here where microinertia, the balance of microinertia, is going to contain a production term, and this might be useful in order to find a link between the two. So this will then be followed by some results, and we finally have some conclusions and outlook. Right, let me start with my motivation. Why do we need generalized continuum theories? In other words, why are we here? Well, we are looking at materials with an inner structure, with inner degrees of freedom, and I took the liberty to cite two people here. Number one citation is from Cemal Ehringen himself, and he asked the question, is it possible to construct continuum theories that can predict physical phenomena on the atomic, molecular, or nanoscales? So in a way, this is an add-on to what was just presented by Francesco. If we have something very complicated on the micro level, can we replace the description of that very complicated structure with a more complex continuum theory with additional degrees of freedom, with additional parameters? And here we have our second quotation by Gérard Morgan. And he says, however, in contrast to those hard-line continuum theoreticians, we personally believe that any relationship that can be established with a sub-level degree of physical description is an asset that no true physicist can discard. So in other words, this is a plaidoyer for more complex generalized continuum theories. Let me give you an example where this has been used for description and used for practical purposes in context with liquid crystals. So materials that need generalized continuum theories are materials which contain an additional internal degree of freedom. And one example for such materials are the already mentioned liquid crystals, which are, as I've claimed here, somewhere in between a solid and a liquid. So first of all, let us look at these cartoons here, which are taken from the book by Chandrasekhar. And what do we see here? We see these digits here. We see lots of digits. And these little digits, they are immersed here, let me say, in another fluid. And originally, they are completely disorderly here. So in effect, what we see here is more or less a fluid with something internal, but in total, it is like a completely unaligned, completely isotropic material. Now, if we apply, for example, an electric field, so that these little digits are aligned, which is shown here. Or if we take a fluid like that and if we make it flow along streamlines, then these digits will be aligned more or less perfectly. Still not as perfect as in case of a crystal, but definitely somewhere in between this isotropic state and this perfectly crystalline state, which is obviously anisotropic. And this can also be seen in these X-ray pictures here, where all of a sudden you have a transition from the isotropic to the anisotropic. So this is the situation we are confronted with. This is what we would like to describe. And here is possible ways of describing that. I will first of all mention the champions of micropolar fluid theories, and actually I give you 4 of them, although I will then dwell exclusively on him and on them. Now, this is Jamal Erringen, as I mentioned already, and we will look at his micropolar fluid theory. And then, in contrast to that, we will look at these 2 chaps here, Jerry Erickson and Frank Leslie. And who else is here? Well, there is Professor Aero from Leningrad. He is here. Why is he here? Well, first of all, he published in 1970, as our friend Victor knows very well, because a whole book was just published in memory of Professor Aero. And this famous 1970 paper on liquid crystals, or micropolar fluids, if you will, is somewhere in between these 2, without knowing what was going on beyond the Iron Curtain. So somehow he is the happy medium here in between these 2 theories, but I'm not going to dwell upon that. I will concentrate on them. And who else is here? Well, there's Pierre de Genet. He is the only one who got a Nobel Prize in this group. Why did he get the Nobel Prize? Well, I say because he really made these structures. Theory alone is good, but not enough. We really need to see things. We must make it tangible. So he was the one who made these liquid crystals and connected them to theory. But the theory he used was essentially from here with a mix of, let me say, Landau theory, in order to study this phase transition, which I have shown before, from isotropic to anisotropic. So these are the 4 champions. Now let us talk about 2 champions only, namely, first of all, champion number 1, Erringen. What does he have to offer? Well, we need a theoretical foundation, and the first part of the theoretical foundation are the balance laws. So I'm going to write down the balance laws a little differently than he did in his book. This is the 2001 book on fluids, Microcontinuum Field Theories by Jamal Erringen. And of course, you know, when you read his books, you can feel he is a solid mechanician. He's not really a fluid guy. You can feel that when he writes it. He likes reference configurations a lot. And fluid mechanics guys don't give a damn about things like that. And I took the liberty to change his equations slightly, so I'm writing them down in a spatial description. So we have, for instance, here the mass balance. Change of mass density is driven by the divergence of velocity, so by the creation of mass, if you will. And we have a second equation here, which is this one. Change of microinertia. Microinertia in the material is also present, the additional degree of freedom. And when we look at this equation, as a matter of fact, if you perform this derivative here in time, you end up with these cross products here of the angular velocity and the J, the microinertia field itself. It's an identity. We are going to change that eventually, so watch out for this equation later on. Then we have momentum, the momentum balance in its standard form. So change of momentum is driven by the divergence of the stress tensor, maybe some body forces here. And on top of that, very important for Erringen's theory, we have a full spin balance. So here's the full spin balance. Here we have the temporal change of the angular velocity, scalar product with the microinertia, and this is driven by the divergence of the coupled stress tensor. We have here the antisymmetric part of the Cauchy stresses, and we have some volume body moment couples in analogy to the body forces which we see here. Last but not least, sometimes not evaluated, but today I promise you we are going to evaluate it, this equation here for the internal energy balance, which serves as a precursor to determine the temperature field in an initial boundary value problem. So change of internal energy driven by heat flux, maybe radiation, and then here these power terms. First one by the stress tensor, the second one by the coupled stress tensor, with complicated expressions here. This is obviously gradient of velocity. Then the angular velocity is also playing a role in creating this dissipative term, and here we have gradients of the angular velocity. What else do we need besides these equations? We need to complement them, as you all know, by constitutive equations. So we need one for the stress tensor, we need one for the coupled stress tensor, this fellow over here, and we need one for the body couples, these guys here. We need maybe one for the internal energy. Surely we also need something for the heat flux, and so on and so on. These are the most important ones which we are going to look at. We're going to look at them now. And of course in this book there is a lot on constitutive theory of these micropolar fluids. I give you the most simple one. The most simple one are linear constitutive relations for an isotropic micropolar fluid. So that was this cartoon, remember, where you had the digits and they were all topsy-turvy, not aligned, and they were isotropic. So here you have the stress tensor. Stress tensor is basically given by what? We have some thermodynamic pressure here. We have this D here. You all know what the D is. Let me just show you this here. The D is of course the symmetric part of the velocity gradient, and then we have this interesting feature here, this H here. The H has something to do with this vector, which is the difference between the angular velocity and the angular velocity we can easily see in a fluid, which is called the vorticity. So this difference is then here with the cross product transformed into a tensor second ring, and this is added here, and that makes the whole thing anti-symmetric, because this W here, as you can see, this has something to do with the anti-symmetric part of the gradient of velocity. So, and finally we also have a linear expression here for the coupled stress tensor, and in the coupled stress tensor the gradients of the angular velocity appear here in this form, and if you look at these two equations, they are more or less alike. So you have the symmetric bit here, you have an anti-symmetric bit, all linear in these variables. So what else do we have? We have body couples. Now, before I mentioned that we might turn on these body couples by some external electric fields. So here is the most simple expression for these body couples. If the matter is not moving, if it is linear, blah blah blah. So this is the most simple one. There are more complex ones in the book. And the heat flux, what about the heat flux? Well, of course, there is Fourier's law. Yeah, we all know Fourier's law. But there is, in addition to Fourier's law, this term here, which has something to do with the gradient of angular velocity. Okay, so these are the constitutive relations I wish to consider in a boundary value problem, a stationary boundary value problem, which I'm going to consider. So before I tell you about the boundary value problem, let me show you the full field equations. These are the field equations here. If you take these constitutive equations, if you plug them into your balances, this is what you end up with. One equation basically its purpose is to determine the field of velocity. And the other equation here from the spin balance, its purpose is to determine the angular velocity. They are coupled here because the W contains the velocity, and of course here is also the omega field in the equation for V. So they have to be solved in parallel. And this is not easy, not for a transient problem. So what are we going to look at? We look at a stationary problem, a Taylor-Couette flow problem. What is a Taylor-Couette flow problem? It is basically depicted here in this view graph. Imagine here this axis, this is one plate, and this plate is fixed. And then this axis up here, this is another plate, and this plate is moving. It is moving to the right. How can we move it? We can move it in two ways. First of all, we can prescribe a certain velocity by which we are moving it. Because we have so many different viscosity coefficients here, it might take sometimes a little more pull in order to get the same velocity on the top. So here's an alternative. We could also say we always use the same pull on the top and see what velocity field we get. These velocity fields are drawn here, and they contain parameters. These equations contain two parameters. First of all, there is one called the coupling number, which is this tau in combination with the usual shear viscosity which we know from Newtonian flow, from Navier-Stokes flow. So if this guy is 0, we are back to Navier-Stokes flow. If this goes to a maximum of 1, we are getting more and more away from Navier-Stokes. So, and there is a second parameter. There are more viscosity coefficients here in the coupled stress tensor. And if you normalize them by the ordinary Newtonian viscosity, shear viscosity, then you get something which has the unit of a length. And this is an internal length scale parameter, which appears here in that theory. So in our particular case, we normalize it, because between the two plates, bottom plate not moving, top plate being pulled at a certain force, constant force, between the two is a certain height h. And so this is our dimensional length scale parameter L, which we can vary in the solution. The solution can be found in closed form. This is the traditional linear Couette flow of Newtonian flow. So we have here Navier-Stokes or Newtonian flow. And you see if this L parameter, if it is very large, if the internal length scale plays no role, then we are again here with a linear representation. If this L is not so large, if it is a value of 5, a value of 2, or very small, we get different curves. And look at the points up here. So the value of 1, the full velocity at a certain pull, we get only here. If we are here with more viscosity, then we cannot, with the same pull, achieve the same velocity at the top. So this is visualized here in this view graph. This is an old view graph. It can be found in a paper by Cohen of 1974, I think. This one is not shown in this paper by Cohen, and I wonder why. This is the angular velocity which we see here. And first of all, angular velocity in the case of Navier-Stokes, you can calculate it in the case of Navier-Stokes. You just have the rigid body movement, so to speak, which is nothing else but a constant at -1 if you calculate it with the flow field which is shown here. If you use a very high length scale parameter, you get essentially the same with some slight departures here. If you make the length scale parameter more and more, then you go to different distributions of angular velocities, to real distributions, not just something constant. If you go to a very small one, you have a linear line again, interestingly, and no angular velocity at all. So this is what you get from this nice closed form solution. But what you don't get, and what was never ever shown in these papers, what about temperature? We have here layers of flow which rub against each other. So this will mean that this is an increase in temperature. Can we calculate this increase of temperature? Well, mostly from the mechanician side, it is not considered at all. They say it's isothermal. Even Ehringen says it's an isothermal flow, which is wrong. It is not true because we have friction. And in micropolar fluids it's even worse. There we have more than one velocity. We have many velocities. The influence needs to be studied. And potentially this is a tooled measurement of temperature to determine these various coefficients which appear in these constitutive equations through temperature measurements. So here's the solution. And I was very proud when I found it because it's closed form. It looks easy in the end, but it is not so easy to find. This is what do we see here? At the top we have a reservoir, fixed temperature. At the bottom we have another reservoir, the same fixed temperature. And in between, temperature can change between one constant value to the same other constant value. This is actually subtracted here. And normalized. So what you get normally, if you consider Navier-Stokes, you get a nice parabola like this. It is symmetric with respect to half width of the height of your channel, and this is this part here which we see. So this is old results which are sometimes by some fluid mechanicians calculated, not always. But here we see the influence of the micropolar fluids after some integration. They contain the length scale parameters, they contain the n, they contain the l, and here you see the influence. Now if you look at these curves, oh, this is interesting, the temperature is less. Why is the temperature less? There are so much friction here, this should be bigger, this should be bigger. It has to do with the normalization. I mentioned already that I'm pulling always with the same strength on the top, with the same pull, with the same force, so that is force controlled, what I present here. But we don't have to do it force controlled. We can also do it displacement control, meaning apply some velocity on the top, same velocity, and let the various coefficients of friction do their job, and then there is a different reference temperature here. It goes with this constant velocity, and all these frictional coefficients, they are inside here, and then you get this. Here is now Navier-Stokes. It is the smallest with the big L. It has the same number with when the length scale parameter plays no role. And if you have smaller and smaller length scale parameters, yeah, more temperature. This is what you would expect. There is more dissipation. So if you draw it like this, yeah, you get what you expect, and it can be, this is the nice thing, calculated in closed form. Right, now let's turn to the second theory, Ericsson-Leslie, or the theory of pneumatic liquid crystals. The balance is first. They are fluid mechanicians, so this is their mass balance divergence of V is equal to 0. They don't have a full J. They have just digits, which cannot even become longer or smaller. They are rigid digits. And they are called directors. So directors, as you always know, they are very stiff, they are very uptight here, and you see here's the director. This is one example of a molecule, MBBA. Here's the director D of Ericsson-Leslie. This is another one, PAA, with a complicated chemical formula in both cases, another director. This is the D field, which we wish to determine. The location, the orientation of the D field is what we are seeking here, what we are looking for here. What do we have at our disposal? We have a momentum balance, good old momentum balance, which we all know. But now, interestingly, what they propose, Ericsson and Leslie, is not the spin balance. They propose a director force balance, which is shown here. Interesting looking equation. Not quite obvious that it has something to do with a spin balance. We shall get into this in a second. Internal energy balance looks like that. So you see a similar term here for the stress dissipation, but for where we had the mu, which was the coupled stresses, this looks now very different. There is the director gradients of the directors and a time derivative. And then there is this funny little g here as well. Let me talk about the constitutive equations, which are necessary in the Ericsson-Leslie theory. What do we need? Stress tensor. Of course, we need the stress tensor. We need now not the moment coupled tensor, we need a relative of the moment coupled tensor, which is the director stress tensor. It is called pi. And then we have director forces. This little g here is a constitutive equation, and we have this big G. This big G has something to do with the volumetric body forces. But what exactly? This is the question. We have the internal energy as well, we have the heat flux, and so on. But, so when you see this theory, you will of course ask the question, well, this equation here with this animal G, with this animal G, and with this animal pi, they appear out of the blue. But luckily, we have the joker in our game. Where does the balance of director force come from? Our joker, Ingo Müller, in his book, Thermodynamics, he gives us an explanation on where it comes from. He takes the total angular momentum balance, specialized to directors. So you have here the ordinary x cross b term from moment of momentum, time derivative, and here you have an additional term because you have a similar contribution, if you will, a spin contribution due to these directors d. On the right hand side you have all the action from the stress tensors. You have the action here from the volume forces, and you have the action here from the body director forces. Now you subtract the cross product of linear momentum from this. This is the linear momentum balance cross product of it. You subtract and you obtain this. Now, when you execute here the time derivative, carry out the differentiation, you get this result. So far we have just one step after the other. We see now this result. We see a bracket here. This bracket will be defined as a force. We call this little g. This is what Ericsson, and they are so similar, Ericsson and Leslie have to say. We obtain, by definition, from making this equal to 0 through an additional g field, which is a constitutive equation, we identically satisfy the spin balance, of course under the condition that this holds. And you see, because of this cross product, it is not unique. This solution which is proposed here is not a unique one. But be that as it may, this is how they do it. Now let us look at the constitutive relations according to Ericsson and Leslie. We have a hell of a stress tensor. Let me show you the stress tensor here. Stress tensor is very large in comparison to the other one which we have seen that before. Why is it so large? Because this is an anisotropic fluid to begin with. These are digits here, and this is for an anisotropic fluid with a D in all kinds of combinations. They appear. We have 1, 2, 3, 4, 5, 6, 7 viscosities. 7 viscosities. This is a hell of a job for an experimentalist. For these two materials which I have shown, these have been determined. We have the director stress tensor, which is not as bad. We have the director force. I mentioned it is also a constitutive equation, and it also has a viscous part, which again contains these viscosities here. We have also a free energy density. It appears already here. Why do we have a free energy density? Because, and this is a true thing, because Ericsson and Leslie, they recognize that these fluids are not just fluids. They have also an elastic energy in them, like an elastic body. And here are, if you will, the elastic coefficients. Lots of them, because they are anisotropic. You have to somehow measure these. Difficult. And this is very different from the other theory which I have shown you before. They didn't have that. So, now we look at the field equations. Field equations, if you plug in the constitutive equations of Ericsson-Leslie into their balance laws, this is what you get. You get a nonlinear equation for this thing here called theta. This is the angle of alignment of the director. So you get this horrible looking equation in context with many abbreviations here. When you determine the angle of orientation of your director, you plug it into this g here, which is some extraordinarily long function with lots of cosines. You plug it in here and then you integrate, and then you find the velocity field. I have done it. Well, actually, I should be fair. There is one guy in the literature, his name is Finlayson, who actually performed this calculation for the materials, which I have shown you, and he plotted this, which I show you here again. So again, it's a shear flow, right? Top is moving with a certain prescribed force, and this bottom plate is not moving at all. What we see here is not the angular velocity. What we see here looks very similar to the angular velocity, but nothing is turning here. The little directors have moved into a certain angular position. This is the angle which we see here. So the angle with respect to the original flow, which is perpendicular here, perpendicular there. People call that the attachment conditions to glass. For glass, these pneumatic crystals, they stick perpendicular to the glass surface. So in between they have some angle. So that's what we get. What and why several colors? Because of this parameter. You have, of course, a lot of choices here. You need to know all the coefficients of viscosity, but then still you have a parameter left which you can change, and this is, if you will, also again a length scale parameter in the theory. Now, how about temperature? Temperature can also be found, but only numerically. And this was done by a young student, Mr. Rickert, and he has used, not this, he has used finite elements for the whole equations, for the whole Ericsson equations, to determine here the temperature profile. They look similar to the temperature profiles I have shown you before for the other theory. Now, the dispute. There is a fight. I hope this excites you, because, you know, I mean, we are waiting for dinner, but when you are in fighting mode, you forget about food. So I'm going to tell you about the dispute between, on the one hand side, pro-Ehringen. We have a Polish guy here who comes to his rescue, Mr. Professor Rimasz, also dead, I understand. So what does he say? He says, first of all, the micro-inertia about the long axis of a pneumatic crystal is zero, and no such physical body can exist. Well, he's right, yes. I mean, this digit does not really exist. It is, as we have seen, a complicated molecule. But, you know, this is a model, so a model is a model. So we must also accept the view of Ericsson and Leslie. This is what I'm saying here regarding this argument. Next argument, the spin balance has a much clearer physical meaning than the balance of director force. True? Yeah, I agree with that. But we have shown there is a connection between the two things, although the connection is not unique. Then, next one, pneumatic crystals are regarded as materials which assume any state that has a uniform alignment as reference state, in which the coupled stress vanishes and only an unknown pressure exists. This is a solid state physicist or mechanician talking here. They always look for this reference state, and they don't find it in Ericsson-Leslie's theory. I'm not surprised that they don't, because this is not the concept of fluid mechanics. And then, this is an interesting one. In many boundary value problems, there are more equations than unknowns. Yeah, it is because it's a simplified theory. It is not complete. There are certain aspects are missing. Also, this thing here, the microinertia tensor, is degenerate. So I'm not surprised that this happened. And then this is the best one. This theory is only a special case of Ehringen's theory. Yeah, I would also say that about my theory. It's just a special case. Now, on the pro-Ericsson-Leslie side, we have Shahinpur, we see him here, and he says, the proposed constitutive laws give rise to inconsistencies between theory and experiments for simple shear flow. Okay, we have to accept that. We always have to test the predictions of our theory with what we see in an experiment. But having said that, we sometimes adjust the parameters of the theory so that they fit the experimental observations. So this is a dangerous lure, what we see here. And then the use of the notion of a reference configuration, which in turn leads to displacement gradients appearing explicitly in the constitutive relations, is something you should not do. Well, here the fluid mechanician is speaking. So I give you a new theory now. Something which might connect both worlds, and it has to do with this here as an application, liquid crystal windows, smart windows. So here's a lady, she switches on and off the voltage here. Sometimes it's opaque, sometimes it is not. I have brought a movie here. I just show you the beginning of that movie. I hope this works. Is this working? Ooh, this is not good. Not good, not good, not good. Wait a moment.
Resonance with your microphone.
Is my microphone? Oh. Maybe you can hear it without the mic. Where is my mouse? This is an English gentleman, and he's going to switch on and off the liquid crystal window just to show you how quickly it goes. This is very interesting. Is there some relaxation and so on? Here he is.
Can you see me okay? How cool is that?
He always asks, how cool is that? And can you see me okay? That's what he's doing.
So it can be transparent, or click the switch and it's opaque. See?
Opaque. Transparent. So it goes like this. It goes very quick. And this is something, of course, if we want to model that, we have to keep that in mind. He's going on and on now in his movie, and he's also doing experiments to measure how much power is used for the switches and so on and so on. Something we may wish to consider if we go quantitative in our description. Here's our description. What do we want to do? 5 fields are sought. Namely, first of all, the density from the mass balance. This is the substantial time derivative, written here as a delta. Then we have the momentum balance. Yeah, we all know that. The J is new here. We have seen it before. This was the balance of microinertia in case of Ehringen. Here is the citation, but now this contains an additional production term. This production term I will explain in a second. The omega, the angular velocity, comes from the spin balance, and the temperature, of course, from the internal energy balance. We know that. The only new feature is this chi. So how can we explain the chi here? Production of moment coupled stress tensor, we know that. Body moment couple. Yeah, here is a possible explanation. We can turn to mixture theory for some illustration what this production term is like. Suppose you are looking at particle densities, here different particles, numbers of species n alpha, and you have a production term which can be due to some chemical reactions. If you sum all the partial balances, you get the total particle balance, and it contains a production term. So this is not zero. It contains what is known as the excess velocity, difference between barocentric and individual species velocity. In the case of the mass balances, you have partial mass balances. If you sum them all up, there is mass conservation, so they have a zero here. So this here with the productions is going to cancel out. How about the moment of inertia? You can write a balance for species alpha. You can sum it all up, but in this case there will be a production term. And here is how it looks like. The production term can have 2 sources. There can be a production because of chemical reactions, and there can be a production because of mutual movement. So very similar to the stress tensors and to the particle production itself. So now comes the simulation, and then we are done. Then we can go for dinner. Cartoon of smart glass. So here's my cartoon of smart glass. Imagine we have these things here in the beginning. They already look almost like these little digits. They are a little chubby. They are not perfect digits, but they can be pulled apart if you can apply an electric field to them. Right now they are just aligned here arbitrarily, so more or less you get some isotropic picture here on a homogenized point of view. Now we switch on an electric field. Then they will all orient like this, and they will also be made longer and longer and longer. And this gives you something anisotropic. So we have a transition from the isotropic to the anisotropic. And we are going to calculate that. Consider these pneumatic digits. One of them, it's a spheroid, so it has a J tensor, a microinertial tensor like that. If we homogenize that, then this would become isotropic on the continuum scale, and under the influence of an electric field from outside, I will take an alternating electric field. They will become more and more aligned and more anisotropic. And we are going to calculate this with a J on the continuum scale, which has two parameters. Little a, which is this diameter here, and big C, which is this diameter. So for a digit, a is dead, 0, and for a digit, this becomes maximum. So here is the simulation. Effective inertia tensor is taken. Temporal development is studied through this balance from the two Jelinas. A changed shape is suggested to give us this production here for the production tensor, which goes in here. And ordinary differential equation results. We can solve that if we insert this electric field. And let me show you the result, all analytical. So here we have a plot. This is the electrical field going up and down in a sinusoidal fashion. This is the A, this is a small radius. So originally everything is isotropic. So we are here at 1. So the small radius becomes smaller, and the other, the C radius, becomes bigger. But then the electric field turns and we go in the other direction. So opposite, and here we have 1 again. So here it is opaque, here it is transparent, here it is opaque, transparent, blah, blah, blah. There is a certain delay, a shift time delay, which is inherent here in these coefficients. But in principle, we have here a very nice cartoon of what is happening in these smart windows. So, and this is conclusions. Extended continuum theories for micropolar theory were presented and revisited. We also showed you a kinetic equation for the moment of inertia, motivated it and analyzed it for the model of the smart glass. In the future, of course, we want to study more complex problems, which most likely will not be possible in an analytical way. Spin balance will always be fully included. Fully coupled problems shall be examined. What can we do? We can study many things. Here, this is the Einstein-de Haas effect, which might be a potential candidate for such applications. Ehringen in his book also says the production of little vortices. This might be something which we describe with such theories. Many possibilities. Time will tell. All what I'm saying is we should look at the unified theory, and we should not just beat ourselves to death. We should talk to each other. So with this, I finish, and thank you for your attention.
Thank you very much for this very interesting talk. I'm sure there are still some questions.
No, they want to eat.
Finally, both theories were not sufficient to describe the smart glass. You had to make it more complicated. Why?
I talked to the people who make smart glass.
Yeah.
What theory do you use? Do you use Leslie's theory? Because it's always said that this is the most frequently used. No, we don't. We do molecular dynamic simulations to find out about the viscosities and the manufacturing processes. That's what they said. So that's the answer. And here is my plaidoyer for a continuum theory. We just have to make it such that it can be easily adapted to technical processes.
So you mean the two others were too complicated for this?
Not complicated. They do not contain certain features. You see, in the case of Ehring and Leslie, they were always directors. They were always there. They were always anisotropic. They were not developing. There was not a transition between isotropic to anisotropic. This transition parameter is sometimes talked about in the theory of de Gennes, for example. He talks a lot about order transitions and order parameters. They have a certain resemblance to this production term. So it should also be very interesting to find out what the connection between the two is. More I cannot say at this point.
I have a question also for the generalized Fourier law that you have.
Yes, Ehringen.
Can you show the equation again?
Yes, it's
the book of Ehringen.
It is from the book of Ehringen. It's the old one, and
there is a new parameter probably to describe.
No, almost there, almost there, yeah, almost there, almost there, almost there. Now wait a minute. Here. That one,
Yes.
that one.
So this alpha is a
For
new coefficient.
no coefficient. In this stationary flow, this term in this two-dimensional, quasi two-dimensional, it's one-dimensional actually, it drops out. It drops out. This has no influence when you study with inverse analysis the one-dimensional flow, quad flow chart.
Use it for your example then. You didn't-
Not in the analytical one, because it is not necessary.
Yeah, okay.
And in the numerical one, which we studied later, we left it out because we do not know what alpha for that
It
fluid
should
is.
be there. Yeah.
Could be there. It could do something.
But this alpha is not a new parameter, it's the same than in the previous equation for the
In which one?
tensor.
In which one?
It's a couple stress tensor.
No. I'm sorry.
Oh, yeah.
I'm sorry. Not the same. Two different books, citations were used here. I used the representation from you from the Cohen citation. I just see it now. Yes, it's a coincidence. Different parameters. No. They also have different dimensions.
Yeah.
I'm sorry for that. Yes. Sorry for the confusion.
Maybe I missed, but what about the boundary conditions for micropolar fluids?
What about the boundary conditions? Interesting. And in the case of here, in this case, of course, you have fluid is glued here to the upper and to the lower plate. So
It means what?
it means that the velocity is actually the velocity of the top plate and the velocity of the bottom plate. And in the case of the omega, we say there is no omega. No omega, up and down, plate moving translationally or not moving at all, no omega. This is the assumption for this solution.
Yes.
Is it again the same justification that J is constant here? Because we assume here J is constant, right?
This drops out completely because we are looking at stationary processes. If I would model this non-stationary, I would have to assume something about J.
And what is J?
J is, in this case, the way I wrote it here, I have used an isotropic J.
That means
You calculate J.
Spherical tensor. But you see, in this solution here, it plays no role because it is because of the semi-inverse ansatz, it drops out completely, no matter what J is. It can even be anisotropic, drops out.
Just a curiosity, there is a variational formulation to get the right boundary conditions for this.
Maybe there is. I have to tell you the truth. I have not studied that, so I cannot answer.
Because no one has done, or because it is impossible?
Impossible it's too, let's say, strong formulation.
Okay. And what did you choose in your final example for key for the production of J?
We will look at it in a second. I just have to run through my slides here. We're almost there. Here it is. This is it. This is the representation for chi. So it depends on the electric field in this manner, and it also contains the determinant of J, because we want this to be present here, that the production should stop when it is when certain limit values are reached here. That's why. So it is a representation theorem, if you say. Depending on two variables, you have the J variable and you have the external field.
Okay, thank you very much for this.